Now, when it comes to the assignments, if you guys want to work on them, like, you know what I mean, you guys are on your own. Please use any and all things at your disposal, okay? And if that means each other, talk to each other, communicate. Of course, I have to say don't copy, because copying, you know what I mean, you're not learning anything. And I promise you, these things there that you're learning in this course, especially this semester. Last semester, I've taught all the courses there in pre-health. I've taught both bios, both chems, both maths, the physics. And last semester, it's more of an introduction. Like the bio was microbiology, right? The chemistry, you know, it only started to kick off until the end. Well, things are going to pick up really quick. You guys have already taken your bio, and I'm assuming there you guys are done bones and muscles, or muscles there this week. That bio, it flies. Do not let that one slide. Every week, it's a different organ system. I've got you guys for physics. I've got most of you guys there for chemistry. If you guys need help there with your bio as well, I've taught all the courses. So don't worry, you're in good hands. There are 5 labs there for this course. They go out 3, 5, 7, 9, 11, and they're due 4, 6, 8, 10, and 12. There are 4 quizzes. I'll have these quizzes there the week before the tests. And the tests here that you can see, they are basically you're having 4 final exams. And, you know, I've been teaching for a long time, and I hate exams. Because an exam is a snapshot of not only what you know, but your ability to regurgitate it out on a particular day, sitting in a particular desk with other students around you and a horrible teacher looking at you with a stop clock. All right? Tests are not indicative of your knowledge. Okay? Like what happened if your kid was sick there last night? You had to take him to Emerge. And you were up till 3 o'clock in the morning, finally got Tom to bed at 4:30, and oh my gosh, I've got an exam at 10 o'clock there this morning, you know. And so how these tests are broken up, there's 4 units. And at the end of, I think it's weeks 4, 7, 10, and 13, these are these final tests. So everything is doable. I know physics has this negative connotation where, it's math, it's physics. Don't worry. This whole program is designed for people who didn't take that chemistry in grade 11 or didn't take that grade 12 physics, which I don't even really understand anyway, because when you're 16 years old, you're expected to make the most important choices of your entire life. Well, no, but that's what they expect you to do. And then by the time you're 21, you've gained some life experience. Something has happened in your life, either positive or negative, which changes the course of your life. And all of a sudden, you know what? I want to be a nurse. Well, dang it. I don't have that grade 11 chemistry. So that's what this course is all about. That's what this physics is all about. And you'll see the way that I've designed it. It's very user-friendly. And I am not one of those teachers there that hates students or hates receiving emails. Bother me, irritate me, hound me, ask as many questions as you can. That's the way I see education, okay? And please don't be afraid to ask any questions anytime, because whatever I think is normal speech may not be the way it goes into your ears. So you might even see a test that was originally out of 40 questions. You might get it back out of 38, because the way I can see my test is, question 23 and question 37, only 5% of the class got right. So that means that there was a problem with the question. I'll cancel the question. I'm always in your guys' favor. So let me know if something doesn't make sense. We'll make it make sense. Blah, 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 blah. And here's the schedule right here. Okay, this week here we're on the study of motion, distance, velocity, acceleration, centrifugal acceleration, and all that kind of stuff. Next week, this is when we start to get moving. Okay, I'll post Lab 1. I will also post Quiz 1 at the end of this class right here, Newton stuff. And then you'll have a week to do the quiz. I'm still working on whether you'll have 1 chance or 2 chance or all that kind of stuff. I'll let you guys know. Okay? But we have the quiz, and then the following week we have the test. Okay? And so this is what we're going to do. This is what we're doing. And then we move on to week 5, week 6, week 7. Okay? We'll have another test. And you'll see here that test 2 covers all material from 4 to 6. So we'll have week 7 lecture, and then after week 7 lecture, I'll post a test. And then you'll have a week to do it, or something like that. You'll have a good amount of time to do it. Okay? And other than that, I think we're all right. If there's any issues, let me know. What do we got here now? I've been receiving some emails about this question, and I apologize if you can't. Darn it. Can I do this or not? Let's go snip. I made a question here. You guys, you'll know there. Yeah, you guys will remember the question there with the boat traveling 12 kilometers an hour north and the truck traveling 10 kilometers south. And what was his name? Sam running on a truck 3 kilometers north, and then he throws an egg off of it. It's pretty silly. Can I share my whole screen here? Where am I looking at? Start, share X. Adobe, share Microsoft. Anyway, can you guys can't see that, eh? Sorry, it's all right. We'll. I don't want you guys to worry too much. That question there, which I'm trying to pull up, I drew a picture of it, but I'll post the picture on Blackboard there for week 1, and I'll send an announcement. For these diagram questions there, it's so important there that you draw a diagram and you know where north, south, east, west is. Because one student asked a great question. One of the questions was, I don't know, I'm just going to make this up, 60 degrees north of west. And the person was thinking there, shouldn't it be north of east? Maybe I have it reversed or not, but it's so important how you draw these diagrams. And I'll post this one there, the boat. Like, if you're standing on the boat doesn't feel like it's moving for your perspective. The only thing that's moving is the truck, Tom, and the egg. You see, everything that's above the boat is moving. If you're standing on the land, the boat's moving, the truck's moving, Sam's moving, and the egg's moving. So it's all a matter of perspective. And I'll post that picture there today, and there on Blackboard. I'll let you guys know that it's there. And just keep plugging away at this stuff. And I'll show you there today that, what have I got here now? I just want to share my screen, and I don't see an option there to share my screen. Is that it? You're sharing, start. What are you guys seeing now? Can anyone turn on their mic? What are you guys seeing?
A black screen.
A black screen. Well, that's not good. So let's stop that. Okay. Anyway, I'll post that there to Blackboard there, and keep plugging away at this stuff there. Today, here we are with lecture number 2. This one's motion. And I've also posted there a formula sheet up to and including week 2. I'll do the same thing there for week 3. And so your week 3 formula sheet, that will include all of your formulas there for the test. So, and I'm very big about that, and I'm very big about giving you guys the answers. Okay, you guys are paying the big bucks. You guys should have all the answers. basically the questions I'm giving you, this is your test. This is your exam. Okay? I'm just going to change the scenario. I'm just going to change the numbers. Probably change it there to a multiple choice. But that's how we're going to do it. Don't freak out about this physics. It's actually, you need to know it to be a better nurse. You have to understand the differences there that's going on between living tissue and dead tissue, and what is happening, what is going on. Generally, the universe goes towards chaos. We eat food to counter that, and we breathe oxygen. You have to think, what gas does a fire need to burn? It needs oxygen. Well, what do you think you're doing to your banana when you eat it? You're burning it. That's why we breathe oxygen. You're burning that banana at a very low temperature, and your body is extracting the fire, quote, as energy, and we utilize the energy there to do stuff. But anyway, the physics is good. Stick with it. If this is your first physics course, so be it, but guaranteed this will be your last physics course. You don't take this stuff in nursing or paramedics or anything like that. Let's rock and roll. Motion. How would you describe the motion of a football being thrown by a quarterback? What factors can affect the football? So, you have a look here. These are good questions. What is affecting the object that you're interested in? What can affect it? What forces are going to act on it? And if you look here, the quarterback would be here, throws the football up. There's this vertical rise and fall. So it's moving from up to down. There is also a horizontal movement. Okay, so it's moving from here to here. So it's moving in kind of two different ways at once. Also, there's a rotation on the ball, right? The tighter the spiral, the more arrow-like the ball is going to fly through, right? So, gravity. And we're going to kind of get into gravity. You know the whole idea there that Sir Isaac Newton was underneath an apple tree and an apple fell on his head. Why do things fall? And gravity all has to do with mass. The bigger you are, the more gravity you have. And gravity is this concept that we're still trying to understand that pulls things towards other things. And you, as an 80-pound person, 120-pound, 180-pound, a 200-pound person, you guys have your own gravity. Would you believe it? You have an attractive force to things around you. Now, because you're only 140 pounds, your gravity, your ability to move things towards you isn't that good. But if you were the size of the Earth, now you've got a bit of weight behind you. Now you can pull things towards you. If you're the size of the sun, look at all the planets there that can't leave because of the sun's gravity. But anyway, we'll get into gravity. I think that's what week 4. Gravity, the wind. Wind can either work against or for the football. The velocity of the throw coming from the arm of the quarterback, and tightness of the spiral. So these are all things there that can affect a football. Just to let you know that there are movies embedded here, links there to YouTube that if I was in class, I would play them, but I can't play them because I'm recording this video and I'm going to post this video to YouTube after, so I can't play the videos here for you and then record the videos because I'm basically doing copyright. So the videos I won't be able to play. So the lecture will be a little shorter than normal, but you guys can play the videos there as you like. Okay. Galileo was probably the first to start to think about. It was before Newton started to think about things fall, and if you think about it, if you're at the top of a building and you got a bowling ball and a banana peel, and you drop them at the same time, which one are they going to hit the ground the same time? Which one is going to hit the ground first? Which one? And initially, you wouldn't be wrong by saying, look, the bowling ball, that's going to fall faster. But they don't. The banana peel, the bowling ball, will actually hit the ground at the same time. And it's kind of a weird thing, and we'll get into all these kinds of things. Galileo showed there that once an object was in motion, no additional force was required to keep it in motion. And we'll get into what friction is. Okay, so Galileo showed that once an object was in motion, it just kept going. It actually liked keeping at the same velocity, right? It liked to keep going. And we'll get, it's a very, very, very important concept there. That objects, things, like to either be two situations only. They like to be stopped, not moving at all, or they like to be moving at the same speed, but we'll get there. What he did was he was rolling balls up and down inclined planes, and he came upon on downward sloping planes, the balls would speed up due to the force of gravity. On upward sloping planes, the balls would slow down. Well, that kind of makes sense, right? These kinds of things are speeding up, and then you push these guys up and they slow down. So something is happening with these balls. They're coming down and they're speeding up. So they're not necessarily happy because they're not going the same speed. And these balls here going up, they're really not happy either because they want to go up at the same speed, but they're slowing down. Something's slowing them down. There's a couple things here that I want to show you what friction is. Friction, when you're cold in the wintertime, you rub your hands together, because the skin cells of your hand actually kind of look like this. Rough, jagged, microscopically, there's little spikes and digs and this and that. And it's the same of what your floor looks like here when you've got a box on it, or just your floor there. That's what, I know your floor may look smooth, but microscopically it's jagged. It looks like Mars. And the box does too. And so when you're trying to push the box along the floor is creating friction. And it's pushing against your pull, which is kind of push. You have to put more effort into it than you thought that you would. Friction can be in many forms here. You've got the friction here on the floor, your hands rubbing together, even meteors coming into the Earth's atmosphere. 99.9% of them never make it to Earth, the ground, solid, because they all burn up because of the air. Like, these things are coming in at thousands of kilometers an hour, and it's hitting the air, and they burst into flames, right? Okay, so this is friction there. Getting back into Galileo, what would happen to a ball rolling on a flat, smooth surface? So there's no more inclined planes, but a ball rolling on a flat, smooth surface without the force of gravity acting on it. So this is kind of a hypothetical situation, right? You had a ball, flat surface, push it, it's moving. It has no friction underneath, because we've hypothetically taken this away because it's a 100% smooth surface, and it's got no gravity acting on it, pushing it down. Galileo found that on a flat, smooth surface, the ball would neither speed up or slow down, but it would continue at a constant speed. Okay? Galileo reasoned that it would roll forever, and the only reason that it would stop was because friction would slow it down eventually enough so it would stop. Like if you slide a puck down a resurfaced ice rink. It'll go all the way down to the end. All right? And then at the end of period number 2, before the Zamboni gets on the ice, you do the same thing there with your puck, and it only makes it halfway down the ice. All right? And sorry if you're not familiar with hockey. At the start of a period, the ice is very smooth and beautiful. And at the end of a period, they've been skating on it for 20 minutes. It's all cut up and bumped and snow everywhere. And the friction would be a lot more. So example number 2, rolling a bowling ball down a freshly oiled lane versus a lane that has been used for league night. So this is what we're talking about here. And what I really want you to take from this slide is, if you take away any type of friction, you push a ball on a flat surface, it likes to go at a constant speed. And it will go at a constant speed forever. Like, I think for my time there, what was the satellite there that was sent out? I think in 77, the Viking mission. And I think 2 years ago, it finally, after 50 years or 40 years, it finally left the solar system. And it's out beyond Pluto now, out into the great unknown. And this thing will go on forever. Because there's no friction in space. There's no atoms in space. That's why space is minus 273 degrees Celsius, absolute zero. There's nothing there, right? So, but we'll get into that there, the chemistry. Galileo noted that objects tended to remain moving without the need for a force. Okay? While objects at rest like to remain at rest. So things like to be moving at a constant speed, not accelerating or slowing down. All right? They like to be at a constant speed, or objects like to be at 100% rest. From this came the very important word inertia. This is a big one. Okay? Inertia, strange word. All it means is a tendency to do nothing or to remain unchanged. So just like what we were saying, objects like to remain at a constant speed or don't move me at all. Property of matter by which it continues in its existing state. Yeah, you can see the same thing right here. Okay. Just trying to think of what movie is this. Bill Nye. Yeah. Ooh, my computer didn't like that. Camera is off. Sorry, something happened. Hey, stop doing that. There we go. Oh my gosh, did this just cancel? Sorry. Hello, is anybody there? Oh, jeez. Hi, are you guys still there? Sorry. Something happened. I don't know. This is the... Oh, jeez. Crazy. Sorry. And... Where is it? Right there. Jeez, man. Crazy stuff. Close. Now, view Ian's share. Really sorry for this. As soon as you start sharing. Okay, are you guys still able to see the PowerPoint? I'm really sorry. They've changed everything around. This is but I can't even see if you guys can. Hi, Amy. Amy Harrison, can you tell me if you can still see the PowerPoint? You can turn your mic on. Alexa Jean?
I can still see it.
Is it? Okay. Sorry, I don't know what you got. Okay, all right. Sorry, I don't know if what you guys are seeing there. Okay. So there's a movie there. I will never touch the movie again. You guys can on your own time. Okay? There's a really good one in there from Bill and I, the science guy. But anyway, what you need to know from inertia is that it's a tendency to do nothing. Or do not change what you're doing. Okay? Here's the inertia. All right? And this is what can happen if you accelerate, or you're going to actually learn there today that there is no word called deacceleration. We're going to get into what accelerate actually means. But what does inertia mean? The inertia of an object is the tendency of that object to remain at rest, or if moving, to remain moving at a constant speed. Getting it back into mass. Now, there's your weight, but then there is your mass. And we kind of use them interchangeably, but in physics, we don't, they're completely two different things. Mass, and you'll have to know this there for chemistry if you don't already, mass is just like if you 5 grams of table sugar. It's just a representation of how many atoms, how many molecules are in that sample. Mass just means the amount. Okay? Weight, this now is a function of gravity. And my weight here on Earth, as I sit here on the Earth's crust, is 220 pounds. But if I went onto the moon, my weight would be somewhere in and around 60, 70 pounds, somewhere in there. That's why, have you ever seen pictures of the movies of the astronauts there on the moon? They're jumping around because their weight is really, really small. Their mass never changes, but because the moon has a lesser gravity, this is how that one works. But mass is a measure of inertia. An object can change its state of motion in one of 3 ways. So here, it can speed up, it can slow down, but it can also change direction. When you change direction, okay, something is happening. Because when you're going straight in a constant speed, there you're not changing. But if you're changing direction, something is going on with your speed. And I'll show you guys this. When an object undergoes one of these 3 changes, we say that it is accelerating. So accelerating, the way we use it in common speech, it means to speed up. But for physics, acceleration can mean speeding up, slowing down, or changing direction. Accelerating just means changing speed. All right? The amount of inertia an object can depend the amount of object I'm only had 3 hours sleep. The amount of inertia an object has depends on the amount of matter the object is composed of. The more matter in the object, the greater its inertia. So, what does that mean? The more matter in an object, the greater its inertia, the greater the amount of energy it's going to take to change this object. And we'll show you what this means here. Like a bigger box takes more energy to push than a smaller box. Makes sense, right? This is just mass and weight. Mass is the amount of matter found in an object. A measure of the inertia an object has in resisting a change to motion. So the more matter that bigger box has, the more ability it has to resist change to its inertia, to its happy state. Inertia, happy state. Acceleration, unhappy. Things really don't like to accelerate, change speed. Things either like to be in a constant motion, constant straight velocity, or not moving at all. Weight, this is a function of gravity. Weight is measured in newtons. All right. 1 newton is the force required to accelerate a 1 kilogram mass at 1 meter per second squared. Ugh. What you have to know, 1 newton is the force to move 1 kilogram. All right. But this test is all open book. You guys will have access to it. And actually, I'm going to put that onto the formula sheet. So I'm going to update the formula sheet. All right. Mass and weight are proportional to one another. Of course they are. If one is doubled or halved, then the other is doubled or halved. So on Earth, a person has both mass and weight. In space, the same person will have the same mass, but will weigh less. Why? No gravity. There is no force acting on that person. So therefore now they're floating all in around the spaceship. On the Earth's surface, 1 kilogram of any material will have a force of 9.8 newtons working on it. So gravity, this is another one, all right? Gravity is equal to negative 9.8, okay? Or 9.8 newtons working on it. So we have a force working down, okay? As we leave the Earth's surface, the force of gravity will begin to decrease, and thus 1 kilogram will begin to weigh less. All right, so as you leave the Earth's surface, we start to weigh less. Interesting fact, my numbers might be a bit off here, but the point will be we boil water here, and water boils on the Earth's surface at 100 degrees Celsius. Do a quick Google search there sometime, and if you were on top of Mount Everest in Nepal, find out what the boiling point of water is on Mount Everest. Different. It's not the same. It's not 100 degrees because there's less pressure up there. There's less grab. So it's interesting. We'll get it. I deal with that in the chemistry there. I think, yeah, this week there is solutions, and I actually talk about that as well. So if you want to hit my chemistry class, you're more than welcome. All of my classes will be posted to the same channel. I have a channel. I have my own YouTube page there, and I just post them there. I think there's a chemistry folder and a physics folder. Even if you're not in my chemistry class, feel free to have a look. You know, I think all the teachers are teaching 97% the same information anyway. Mathematical conversions. There's a formula. Force is equal to mass times acceleration. All right. If you know the mass of an object in kilograms and want to find its weight in newtons, simply multiply the mass of the object by a factor of 9.8 newtons. So Sam has a mass of 65 kg. By the way, just to let you know, the 1 kilogram is equal to 2.2 pounds. All right, 1 kilogram is equal to 2.2 pounds. So you can, if you know your body weight in pounds, you can convert it to kilograms. You'll actually have to do that, I think, lab 4. But Sam has a mass of 65 kg. What is his weight in newtons? Well, force is equal to mass times acceleration. 65 kg times 9.8 newton kilograms is equal to 637 newtons. If you know the weight of an object in newtons and want to find the mass, simply divide the weight. So it's just the same formula. Okay, in the first question here, we gave you these two. You solve for force. And I think for the second one there, we gave you force and acceleration. And you got to solve for mass. It's just, this is a triangle formula. And if you're in my chemistry class, I'm big about these triangle formulas. And if you have any issues there with mathematics, email me and we'll get you guys through, because you got to be able to flip these formulas around, and I can show you how to do these. Okay? Test yourself. Again, I'm not really fooling around like with the answers. You guys got the answers. I am interested in you guys and your comprehension, being able to take this and apply it there to a test. So question number 1, if we compare a 2 kilogram bar of gold to a 1 kilogram bar of gold, will the larger bar have twice the inertia, twice the mass, twice the weight, if measured in the same place? And the answer is all of the above. So a 2 kilogram bar of gold compared to a 1 kilogram. It's going to take twice as much energy to push this thing. So therefore it has twice the inertia. It has twice the mass. We know that. 2 kg to 1 kg. And twice the weight. Well, if they're measured in the same spot on planet Earth, they will. The 2 kg bar will have twice the weight. So that's a good answer, D. How does the mass of a 2 kilogram bar of gold vary with location? The mass will not vary with location. Mass never varies. Okay? Its weight will vary. All right? Depending upon where the bar of gold is. On Earth, on the moon, this kind of thing. Question number 1 again. If we compare a 2 kg bag of feathers to a 1 kg bar of gold, will the feathers have twice the inertia, twice the mass, twice the weight? They will have all of the above, because 2 kg of anything is 2 kg of anything. And 2 kg is compared to 1 kg. It doesn't matter if it's feathers, gold, chocolate, whatever. Okay? Any issues with that? Let me know. This is a really good one here. I think this is from the second movie, which is actually Star Wars 5. Really good. What is the Force, Luke? So have a look at that video. I can't play it here, but there is something out there, and it's called Force. And it's undetectable as far as predicting it, but there are forces that play right now all around you that's keeping your life in order. As we have seen, a force is a push or a pull. That's all a force is, which will cause an object to either speed up, slow down, or change direction. So if you're driving along the highway and you have cruise control on, and let's say a car comes and applies a force to the back of your car is going to speed up. It's going to accelerate. It's going to change speed. Okay? Maybe a deer comes out there 50 feet there before your car, and you hit the brakes. Your car is accelerating. It's slowing down, but it's accelerating. All right? And that's a force that's been applied, which is slowing your car down. When we use the term force, we are implying a net force. And this includes all the forces at play. So net force just means this force plus this force plus this one plus this one. If you add them all together, this is the direction that the car is going to go after it's been hit. All right? It's just the resultant force. If you add this force, this force, this force, and they're all acting on the car at the same time, the car is going to go this way. So that's what we'll call there the net force. And I'll show you this right here in the next slide. So here we've got a ball, and let's say I apply 5 newtons of force in this direction and 5 newtons of force in this direction. Well, because it's kind of like last week there, with the vectors. You just add them up when they're going in the same direction, and therefore the ball is going to move. It's going to have a force of 10 newtons applied in this direction, movement. Here I've got 5 newtons of force applied on the ball in this direction, 5 newtons in this direction. They're going to cancel each other out, so therefore no movement. And then here I've got 10 newtons of force being applied in this direction, 5 newtons of force. So therefore now the 5 here will cancel 5 from over here, and therefore now the ball will move 5 newtons in that direction. So that's just, it's all based on last week there, and you can add these forces up. And so these are your applied forces. This is your net force. The forces shown in the previous examples are known as vector quantities. Vector quantities have both magnitude, great word, means how much, how strong. It's a number. And direction, north, south, northwest, these kinds of things. A zero net force does not mean that an object is necessarily at rest. What it does mean is that the object's state of motion is unchanged. All right, I'm going to read that one again. A zero net force, it can mean that an object is at rest, but it can also mean that the object's state of motion is unchanged. That means there that the object hasn't been exposed to a force that is going to cause it to accelerate, change speed. This means that it can be at rest or moving in a straight line at a constant speed. So zero net force means this. You might see that one again. When the net force of an object is zero, we say, so in this case here, when the net force of an object is zero, we say that the object is in a state of equilibrium. Equal forces are acting in opposition to each other. So there's no forces there that are causing this object to accelerate. So this thing is either sitting on a tabletop, not moving at all, or this thing is rolling at a constant speed, not speeding up or not slowing down. So it's, okay? So play with these things a little bit, and all you can do is just ask questions. Ask as many questions as you can, okay? This is a pretty important slide. It kind of sums up what we've been talking about there the past couple slides. The whole idea of an object being in equilibrium. There is no change of speed. There is no acceleration. Okay? Achieved when an object is in a state of rest or is moving in a straight line at a constant speed. Equilibrium happens in those two situations only. Objects at rest are said to be in a state of static equilibrium. Please know that. Objects moving in a straight line at a constant speed are said to be also in equilibrium, but this one here we call dynamic equilibrium. So static equilibrium means it's at rest. Dynamic equilibrium means that it's moving in a straight line at a constant speed. It's not accelerating. And you notice there that I say in a straight line, because as soon as you move away from a straight line onto a curve, you are now changing direction. And by definition, if you are changing direction, you are changing speed. So therefore, as soon as you're not moving in a straight line, you are accelerating. Okay? Two good ones there. Force of friction. Friction occurs whenever two or more objects pass over one another. Okay? And can be solid, liquid, or gas. When two things rub together. Solids can rub together, liquids can rub together, and gases can as well. Friction always occurs in the opposite direction of the motion. So you're pushing that box along the floor. Well, the floor is pushing back. It is. I know it's hard to believe that the floor is pushing back at you, but it is. Friction is present between all surfaces regardless of their respective smoothness. Okay, remember there that even though your hands may be smooth, microscopically, they are jagged. And there's your friction when you rub your hands together. And the amount of friction depends on the objects involved and how hard they are pressed against each other. Oh, there's my Bill Nye the Science Guy. So when you guys watch this video again, please have a look at the videos. Bill Nye, I love him. Love him. Love him. The guy is one of the best people on the planet. And as far as I know, as far as his science goes, his videos out there are easy to follow. And this one here, I think, is about 20 minutes. You don't have to watch the full thing, but you can. It's Bill Nye. Test yourself. If you push a chair across the floor in a straight line at a constant speed, it is in a state of dynamic equilibrium. There are two forces acting on the chair: the force of your push and the force of friction. Which force is greater? If you're pushing the chair across the floor in a state of dynamic equilibrium, what does equilibrium mean? It means no forces. Whenever you see the word equilibrium, it means no forces. So this question is actually kind of a trick question when it says which force is greater. Okay? Whenever you see dynamic equilibrium or static equilibrium, it means that there is zero net force. And they are equal and opposite. Suppose you exert 100 Newton force on a heavy crate resting motionless on the floor. The fact that the crate does not move indicates what about the force of friction? So you apply a force to a heavy crate. The crate no movie, doesn't move. What's going on with the force of friction? Pushing back against the box. Since the crate is not moving, this tells us that it is in a state of static equilibrium and thus has a net force of 0, right? Therefore, the force of friction has to be greater than this 100 newtons. Has to be. Because if you're not moving, if you're putting 100 newtons of force on that box and that box ain't moving, well, the force of friction is gotta be greater than the 100 newtons. What do we got here? What's going on? There we go. Whoa, weird things happen in there today. Continued from number 2. So let's go back there to the box there that we just applied 100 newtons to, and it didn't move. Aha. Well, what if you pushed harder and you produced a force of 115 newtons on that box, and then wunderbar, the crate moves. And it moves in a straight line at a constant speed. How much friction is now acting on the crate? So if it's moving in a straight line, constant speed, dynamic equilibrium, has a net force of 0. So, but therefore, the force of friction must also be 115 newtons. If you're pushing this box across, it's not picking up speed. The 115 newtons worked. This box is now moving in a straight line at a constant speed. Dynamic equilibrium, 0 net force. The force of friction is also working against your 115 newtons. It's canceling it out. That's why it's not speeding up. Number 4. What force does a sliding crate experience when you exert a force on it of 125 newtons and the force of friction between it and the floor is 115? So here, we applied a force of 115. The floor was pushing back at 115, so therefore now the box is moving, but it's not speeding up. It's dynamic equilibrium. We'll have a look here now. I'm applying a force of 125 newtons. The force of friction pushing back is only 115 newtons. So now we've got a force of 10 newtons. Remember this one right here? Sorry, just cancel that. Don't look at that. But here we've got this force of 10 newtons going on. So we have movement, and not only do we have movement, where'd that go? Where did it go? Right here. The resulting net force will be 10 newtons. Therefore, the crate will be picking up speed. So we are not in a state of equilibrium here. Not static, not dynamic. There's actually a real force being applied to this thing. So now this crate is picking up speed. It's accelerating. It's getting faster and faster and faster. So that's what we're talking about there. Good little questions there to make you think. Sorry if it's not that exciting. It'll get exciting. There are some good things for this course. Not a lot, but it's all right. Getting into speed. I love this little formula here, little triangle formula. Okay, it's on the formula sheet there. I'm sure you guys have all seen this there. Speed is equal to distance over time. And these little triangle formulas here, speed, distance, and time. And how I do this is whatever you're looking for, put your thumb on top of it. So if you want to solve a speed question, put your thumb on speed, and what you're left with is distance divided by time. If you put your thumb on time, time is equal to distance divided by speed. If you put your thumb on distance, distance is equal to speed times time. Just an easy way of utilizing these triangle formulas. If you have any issues with that, just email me and we'll get you sorted out. You get all the basics going, and then I'm sure you guys will just take this and just run with it. Galileo was the first person to describe speed in a mathematical way. He simply compared the distance an object traveled with how long it took to get there. So I traveled 100 kilometers and it took me an hour. Well, that's 100 kilometers per hour. We use this even today, and it's called average speed. And what this means is if you drive from here to Toronto, okay, or I'm in Barrie, so if you drive from Barrie to Toronto, it's about 100 kilometers. And it takes me an hour. But am I driving 100 kilometers the entire way? I could with my cruise control. But, you know, I sometimes let it go up to 115 and then back down to 90. And I stopped at the gas station there to get gas. So there's all these other factors that are involved. But if it took you an hour to travel 100 kilometers, then officially your average speed over the course of the trip was 100 kilometers an hour. You see down here, example, if a car travels 120 kilometers in 2 hours, speed is equal to 60 kilometers an hour. Find the average speed of a person who traveled 50 meters in 12 seconds, then 100 meters in 15 seconds, and then 210 meters in 45 seconds. So, have a look here. Your speeds, add them up. Or sorry, your distances here, 50 meters, 100 meters, 200 meters, add them all up. And then you divide all your times together. Sorry if you can't see that. There you go. 12 seconds, 15 seconds, 45 seconds. And you add them all up, divide them, and you get 5 meters per second. All right. Here's another average speed problem. Find the average speed of a car that takes 51 minutes to drive between marker posts 45 kilometer and 147 kilometer. So basically what you're saying, it takes 51 minutes to travel this distance. Well, what distance did you travel? Well, you were at marker 45 and 147, so that's 102 kilometers. Okay? But this question here is asking for this in kilometers per hour. Well, I don't have hours. I got minutes. So a thing in the physics there, holy, is it ever snowing out? I'm in Barrie. Geez, I can't even see across the street. Crazy. But how this works is I might give you an answer in minutes and want it in hours. I might give you an answer in meters, want it in kilometers. So you'll have to be able to convert very fluidly. And just an example here, in order to use this formula right here, I need time, all right? And what we've got here, 51 minutes over 60 minutes is equal to x over 100. Because basically, I need to know what percentage, if 60 minutes is an hour, well, that's what I need to find. Because the question is asking this in kilometers per hour. Well, I've got 51 minutes, so what percentage is 51 minutes of an hour? So, if an hour, 60 minutes is 100%, 51 minutes is equal to x. Cross multiply. So 51 minutes is equal to 0.85 hours. Okay? So 51 minutes is equal to 85% of an hour. This is what we're, so now we have a number that's in hours. So speed is equal to distance divided by time. Your distance is 102. Your time is 0.85 hours. It's not even a full hour because it was 51 minutes. And your speed is 120 kilometers per hour. Any issues with that, let me know. Okay. Speed is relative. Do you remember Sam on the boat or Sam on the truck, on the boat, on the water? Speed is relative. If you're sitting on the boat, the truck and Sam and the egg are the only things moving. Because you're sitting on the boat, you're traveling at the same distance as the boat is, so anything else that's moving, all right, looks to be moving. And it is. But right here, look at these examples. Relative to the water, Sam would be traveling at 28 kilometers an hour. And see, Sam is running on at a speed of 8 kilometers north on the deck of a cruise ship that is traveling 20 kilometers north. So Sam is running 8 kilometers in this direction. The boat is traveling 20 kilometers in the same direction. So relative to the water, you're looking at, if you're on shore, Sam is moving at 28 kilometers an hour north. Okay? But if you were standing on the boat, you're traveling at 20 kilometers an hour just like the boat is, so that's canceled. The only thing you see moving is Sam at 8 kilometers an hour. If that gives you guys trouble, again, let me know. Okay? Instantaneous speed. We can calculate this. The speed of an object at a precise moment in time. And this is based on, your speedometer there in your car. It measures instantaneous speed. So what is the instantaneous speed of an object that traveled 1 meter in 0.05 seconds? Well, same formula. Distance divided by time, 1 meter divided by 0.05 seconds is 20 meters per second. All right, okay. You guys can test yourself here. What is the average speed of a cheetah that sprints 100 meters in 4 seconds? Bang. How far will a car travel if it travels 60 kilometers an hour for 4 hours? So this one here, how far will a car travel? What are we looking for? Speed, distance, or time? We're looking at distance. So you put your thumb over distance. Distance is equal to speed times time, which is what we have here. How long will it take a runner to travel 120 kilometers if she runs at an average speed of 5 kilometers per hour? So here, how long will it take? Here we're looking for time. Oh, and calculate the instantaneous speed of an Olympic sprinter if his time was 8.6 seconds at the 80-meter mark and 9.58 at the 90-meter mark. Have a look at these, make it make sense, and if they don't, shoot me an email. Speed and velocity are not the same thing. you'll remember these words here, scalar and vector, from last week. Speed is a scalar term. Strength, how fast, 50 kilometers an hour, magnitude, but no direction. Velocity is the same thing, 50 kilometers an hour, north, has a direction. And we can use this formula here. When we talk about speed, we talk about how fast, but when we talk about velocity, we talk about direction and speed. And here you've got velocity is equal to distance final minus distance initial divided by time. These formulas are not bad. You don't have to remember them. On the day of a quiz, on the day of a test, you're going to have all of your things, you're going to have your formula sheet there. You're going to have everything ready to go. You don't have to memorize these. You have to memorize how to use them. All right? And that's what we're working on. Constant speed means not speeding up and not slowing down. Constant velocity means constant speed, not slowing down, not speeding up, but in a constant direction. A straight line with no acceleration. So both of these guys here where there's no acceleration. Okay? An object is traveling 3 meters per second. How fast is it traveling in kilometers per hour? This one here, you have to be able to do this. And you have to be able to convert seconds to hours, minutes to hours, hours to minutes, hours to seconds, meters to kilometers. Okay. Actually, what I will do is I'll post another little thing there for meter. I'll post something there that will help you convert meters to kilometers and these kinds of things. If you have a look at this, 3 meters per second. And we want to know how fast is it traveling in kilometers per hour. Well, I got meters and I got kilometers. Okay, so 3 meters per second, I got to change that to kilometers. So how do I do that? How many meters are in a kilometer? All right, 1,000. How many seconds are in a minute? 60. How many minutes are in an hour? 60. So how many seconds are in an hour? 60 times 60, 3,600. Okay, so this one here, I can't emphasize how important this is to be able to do. Okay, a simple question. I could, a distance is equal to speed over time, and all of a sudden at the end of it, I could ask for it in kilometers per hour. So therefore now your final answer that you just calculated in meters per seconds, you gotta take an extra step and convert everything. All right. Let me know if this one here gives you trouble. I got lots of stuff on things like this converting. Acceleration. Now we are changing speeds. Okay, moving objects can either speed up, slow down, or change direction. When one of these occurs, we say that the object is accelerating. Acceleration is equal to velocity final minus velocity initial divided by t. So it's basically the same formula as that one. All right, but we're doing this one right here. Okay, so a lot of these formulas are kind of the same. They just change what's the word I'm looking for? The letters around. Okay, same formula there for velocity. Here we've got acceleration is this one. So, and we've got a question here. How fast does a car accelerate if it goes from 0 meters per second to 30 meters per second in 5 seconds? So you're looking at this going accelerate. Okay, and I've got 1, 2, 3 bits of information. It's got to be this formula right here. All right? Because you think about it on a quiz or a test, you don't know what the next question is going to be. All right? It's all mashed potatoes. I'm going to try and go linearly straight up week 1, week 2. but we'll see how it goes. And you don't know what question, you don't know what formula is got to come that you need to use for that question, but you've got all your formulas there. Try and pick apart the question and figure out what formula you need. That is the whole game to this exam and the chemistry as well. What formula do I need to solve this question? All right, and if you look at this right here, how fast does a car accelerate? Okay, there's a couple formulas there for acceleration that we'll get into. And right here, and once you've got the formula, you just plug and play. And by the way, now that I mention it, I said this there to my chemistry. I think I also said it there last week as well. Please, please get a scientific calculator. Okay? You can get by on an Apple phone or your calculator phone, but I've seen students, and I mean a lot of them over the years, make mistakes. And generally, how these tests and quizzes go, they're not. There might be some written out answers that I may get you to do as far as assignments go, and written out answers, I have the power vested in me to give out part marks. So let's say you do a question and it takes you, half a page to do, and at the very end your calculator spits out a wrong answer. Well, okay, the right answer was only worth 1, but I wanted to see all your work and the whole question's worth 5, so you get 4 to 5, even though you got the wrong answer. I have no problem doing that. But these tests, these quizzes are going to be multiple choice, man. So it's right answer or not. So I don't want to see any calculator mistakes. So please go up for 10 or 12, 15 bucks there. Go and get that because you'll need it for the chemistry as well. I swear. Okay? Because in chemistry, physics, we deal with huge numbers. Like the mass of the Earth in kilograms. You know what I mean? That thing must have like 16 zeros behind it. Or we deal with things that are very, very, very small. That'll have 16 zeros in front of it, like the mass of an atom. Okay? And so when we get into scientific notation, which we will, all right, please make sure you have a scientific calculator. The most important button on that calculator is the EXP button, or sometimes it'll be written times 10 to the exponent. All right? Any issues with that, let me know. Here's another acceleration question. If we increase the speed of a car from 35 km per hour to 50 km per hour in 3 seconds, what is our acceleration? And then here, what is the answer in meters per second? So here, I gave you all these there in kilometers per hour and 3 seconds. You got to convert everything. All right, so you plug and play. That's how you found the right formula. You plug the information in, and your final velocity, initial velocity, 50 minus 35 divided by 3. And we've got kilometers per hour per second, but I want this there in meters per second squared. Try that out. And if maybe later I'll post and see how to do this, but try this out. See if you can convert the acceleration, which is a right answer, 5 kilometers per hour per second. See if you can convert that into that. You're going to have to play. You've got kilometers. You need to change to meters. And then you've got hours. You need to change to seconds. You've already got 1 second here. You only need to convert that one there to seconds. Try that out. That's some good math. And if I get a lot of howls on email and tell me if it's giving you trouble, I just might post that anyway. Okay, so post, insert, what is that? Slide 35. Good. Test yourself here. It's just more of the same. Car accelerates from 20 meters per second to 25 meters per second, 4 seconds. Find the formula, plug and play. And in 2 seconds, a car increases its speed from 60 to 65 kilometers per hour, while a bike goes from rest to 5 kilometers an hour. Which has the greater acceleration? You just plug and play. I've given you everything you got here. So you've got the car, 65 minus 60 divided by 2 seconds. It's all there. gives you an acceleration of 2.5 km per hour per second. The bike, 5 kilometers an hour. What was its initial velocity? While a bike goes from rest. So that means that its initial velocity was 0. Okay, so it says 5 minus 0 divided by 2. And as it turns out, they both have the same acceleration. Okay. While an object is slowing down, its speed is decreasing. Okay. Still acceleration. I know it's weird. We're programmed to think that acceleration means to speed up. It just means to change speed. Even I get confused, when I teach the course, but when I go out into public and I tell my 7-year-old there that we're slowing down, we're accelerating, she looks at me like I'm weird. And yeah. So right there, we do not use the word deacceleration. I don't even think that is a word. And again, just another... I'll tell you a trick to these. The hardest part about these questions is the English. Is the ability to take this information and pull it out, find your formula, the right formula, plug the information in and get an answer. Something happens, and I don't want this question here to be difficult. What is it asking? After a race, a runner traveling in a straight line takes 5 seconds to come to a complete stop from a speed of 9 meters per second. What is the runner's acceleration? Okay, so I'm looking for acceleration. So now, go and get you have your formula page. Okay, so it's this one, this one, this. Okay, so it's possibly 4 formulas. Okay, it takes 5 seconds to come to a complete stop from a speed of 9 meters. So... what is my final velocity? Well, it comes to a complete stop, so it has to be 0. And the initial velocity was 9 meters per second. And you just plug it in and have a look here. Look at my acceleration. Negative 1.8 meters per second squared. Means it's slowing down. All right, so the only difference, acceleration just means changing speed. A positive acceleration means you're speeding up. A negative acceleration means you're slowing down. Okay. Free falling. If we drop a rock off of a cliff, funny spelling of off, the only force that is acting on it is the force of gravity. Well, not so, because you also have a bit of friction pushing back up, but majority of the force is the gravity pushing it down. And we say that the rock is in a state of free fall. All free-falling objects accelerate at a rate of 9.8 meters per second squared for every second there that they fall. So there's your gravity. All free-falling objects accelerate at 9.8 meters per second squared. For free-falling bodies only, the distance of an object free falls from rest. So this is like at the top of the Leaning Tower of Pisa there from their previous slide, and you got a bowling ball and a banana peel. Okay, this is where you would use this formula, where distance is in meters, acceleration is gravity, 9.81 meters per second. So that one there is given. That one there, that's your acceleration, and time is in seconds. So you'll see there that after 1 second, the object has fallen 4.9 meters. 2 seconds, 19.6 meters. 3 seconds, and you see this thing is speeding up, accelerating. And don't forget, you'll need these there for number 15 of this week's review questions. We're almost at the end. You've got this one right here. This is basically the same formula that you saw there before, and where velocity is equal to gravity times time. Okay, so you guys can have a look at that one there. We've got the last, I think the last part of this is something called centrifugal force. And this is if you tie a ball on a string and then start spinning it around above your head. all right? Or like a cowboy's lasso or something like this, okay? This is also acceleration. And if you think it's not, I would show you the video right now, but I can't show you the video. You guys can watch the video. But this whole idea of acceleration basically on a string, this includes, this is basically all about the change in direction. And the acceleration of an object moving in a circular path is called centripetal acceleration. The magnitude of the centripetal acceleration depends on the velocity and the radius of the curve that ball is traveling on. And so many people have a hard time accepting the idea that this circular centripetal acceleration, because they do not see changing the direction of motion as an object in the same as changing its speed. But if you have a look at this little experiment here, if we can kind of go through it there in words. If you place a book on a bus seat and watch it slide around on the seat in response to the bus acceleration. So let's say the bus is at a red light and has its left blinker on, and then it turns left. Which way is the book going to slide? As the, I'm just reading right here, as the bus speeds up, the book will move backwards. So how this centripetal acceleration works, it works in the opposite direction. As the bus slows down, you ever notice that we kind of come forward, in our seat, even though that's why we wear seatbelts. Because if we're in the car and the car is traveling at 60 kilometers an hour, it doesn't feel like it. You remember, you go back to Sam, the truck, the boat, the egg. If I'm sitting in my car and my car is going 60 kilometers an hour, I am traveling 60 kilometers an hour. But it doesn't feel like it because I'm moving the same as the car. That's why when you're on the ship, you negate it from the equation. The only things that are moving are the truck, Sam, and the egg. Any issues with that, let me know. But as the bus slows down, the book will move forward. That's why we wear seatbelts, because if we didn't wear seatbelts, we're traveling 60 kilometers an hour, and depending upon the amount of breakage that we use, you'll go flying. Please wear your seatbelts, and also the driver, please make sure that everyone is in the car is wearing a seatbelt, because 3 people wearing seatbelts and 1 person not, that 1 person is very dangerous. Did you know that if you had an empty Kleenex box in the back of your car and you slam on the brakes and that empty Kleenex box hits you traveling at 40 kilometers an hour, it will knock you out? Could you imagine a 100 kilogram human being flying at you in the middle of a car turning over? So, in all cases, the reaction of the book is the opposite direction of the acceleration. So if the bus driver turns left, the book is going to fly right. If the bus driver puts on the brakes, the book is still going to go forward. If the bus driver hits the gas, the bus jets forward. We all go back into our seats. Okay? So let's have, this is really good. And there's another video here as well. Oh, I wish I could watch them. But you look at race car drivers. And I mean NASCAR. You look at Formula 1. You don't think of these people as being fit. But these people who drive Formula 1 and NASCAR and all those crazy souped up cars, they are mucho fit. Crazy muscle on them because of this centripetal force. And G-force is a word that we use. It's more of a space word, but it's the 1 G-force is basically 1 amount of pressure, 1 atmosphere of pressure. Okay? And these race car drivers, you'll watch the video there, they're reaching upwards of 6 and 7 and 8 G-force. Crazy amounts of force. And because when you turn on a bend, watch the video and you'll see it. And it's actually really quite amazing to see. So have a look at those two videos there on centrifugal acceleration. And again, the questions here. The hardest part about these is pulling the information out of this garbledy-goop words and then finding the right formula. Once you've got the formula, once you've pulled out the information, it's just a matter of plugging and playing. Okay, so have a look at this. What is the acceleration of a car traveling at a constant speed of 10 meters per second as it goes around a curve with a radius of 20 meters? Well, it's asking for acceleration. You've got a couple formulas there for acceleration. I'm going on a curve, probably centrifugal force. Okay, all right, so this is the formula I use. Acceleration is equal to velocity squared divided by radius. 10 meters per second squared is 100 divided by the radius, which is 20. So your acceleration is 5 meters per second squared on that curve. What happens if we double the speed? So we're not traveling at 20 meters per second. We're traveling at 10 meters per second. We're traveling at 20 meters per second. And you'll notice that if you're driving on a curve, on an off-ramp or on-ramp onto or off the highway, sometimes when you're going too fast, you tend to veer off the road. So you got to slow down a bit to maintain the curve on the road. So if you have a look here, if you double the speed, you're also you're quadrupling the acceleration. This was 5 meters per second. This one here is 20 meters per second. Now you're starting getting into dangerous stuff. Your speed is changing too fast on that curve. And what happens if we double the radius? So we have same 10 meters per second, but now our radius is 40 meters. Your acceleration is half as much as original. So it's safer. Okay. These are really good. I like doing these. It just can't be all about math. It has to be about, understanding. And if you just go through these little definitions here, they're not bad. The quantity of matter in an object is mass. The force on an object due to gravity is weight. Push-pull is a force. Property of an object to resist change in motion. I love the word inertia. The scientific unit for force is Newton. Combination of all forces that act on an object, net force. A quantity that requires magnitude and direction, vector. Resistance, force that opposes motion with contact, friction. Force of friction acting on an object in free fall, air resistance. Distance traveled per unit time, speed. And here we've got velocity, acceleration, centripetal, and gravity here. So you guys can have a look at this stuff. It's really not that bad there this week. You've got the formulas there. It's just a matter of plugging in and playing. The questions there that I provided, you've got the questions and the answers. I recommend hitting them all. Not today, of course, but take your time. Hit them all, try them out. Make mistakes. That's what it's all about. Make as many bloody mistakes as you can. Just never stop. And if you're not getting something, email me. Okay, and we'll get you sorted out. Quiz 1 next week. Labs begin. And next week we are on to Sir Isaac Newton. So if I hope that that is all right. If anyone wants to stay on, if you guys have any questions at all, but this is the video there that I'm going to post onto YouTube. I'll post it up there, and I don't know, whenever I finish up here. But other than that, I wish you guys all the best. Please be safe out there. Keep in contact with me. And if you're having any issues, just let me know, and we'll get her done. Okay? You guys are important to me, and I want you guys getting out of here with all A's. Come and get it. Other than that, I got nothing. So you guys are free. Go and make a snow angel outside. It's beautiful out. Thank you so much, and have a great day. Again, anyone staying on, if you have a question or two, it's all good. Thanks, guys.
Thanks, Ian.
It's all good. Okay, so where is that? Is that it right there? Set like that. Now, God, they've changed everything. Now, if anyone there, yeah, I don't know. I can't really tell how many. It's crazy. But if you guys have any questions, just shout them out. Talk to me. It's kind of free for all now. And even there this week, I'm still working on how to share and all this kind of stuff. But if you guys let me know what questions you are giving you trouble, or if anything's giving you trouble, it's all good.
If you have a second, can we talk about the one with the egg and Sam from last week?
Sure. That would be great.
I don't know if you remember me, but I've emailed you about 3 times for the explanation of the questions.
I did see that there yesterday, and we.
I resent it because I didn't know if it sent, but I sent you a long
Yeah,
email.
yeah, I got it. It's just last night and there this morning, it was kind of a bit of hell on wheels to get everyone organized there for hospital and all that kind of stuff. But I did see that, and what I'm going to do is, I don't know, is my camera still working?
I see a black screen and I can't see you either.
Oh, I hate this thing. So you guys couldn't even see me the whole time. That really hurts my feelings. Let me see here.
I think we saw you until you tried to click on the video.
I know, that was horrible. That was really dumb. Here, I'm actually going to pause.